Lecture 32, Disk Scheduling. Well, you're tired now, I'm sure, of hearing me say it, but the disk is a very slow device as far as the CPU is concerned, and, I'll get to it eventually, I'll service the request later, but the CPU and the hard drive have very different definitions of later, now don't they? We're going to examine the hardware behind magnetic hard drives and see why they're slow, and consider what we could do to schedule requests so that work gets done in the most efficient way possible. It's not magic. It can't overcome the fact that the disk is very slow, but there's bad and then there's worse. If you are fortunate enough to be able to attend this lecture in person, and I'm clever enough to remember to bring it, I have a magnetic hard drive that failed on me. This would be, 2014 or so, when it failed, and I've now disassembled it so you can play around with it and tinker with it if you want. So, unless you have a solid-state drive, which I'm certain that you do in your computer, it's the mass and permanent storage of data is on a magnetic hard drive. Back before those were common, you would frequently have this, like even in your laptop, a magnetic hard drive, and even then, maybe one that isn't even that fast, all considered. And due to the physical nature of how disk drives work, there is an associated delay whenever we want to move around to a different location. We'll see why we talk about the physical locations in a minute, but they are mechanical devices, right? Like physical pieces of stuff have to move from one point to another, and this movement takes non-zero time. So, given that, we want to devise efficient schedules for reading and writing. And these really only make sense when we're talking about a magnetic drive, right? For SSDs, monies can in fact buy you time, and these are, all things being equal, much faster and much easier and better to work with. SSDs do not contain any moving parts. That's why they're called solid-state drives. That's where the name comes from. That is to say, they have no physical components that need to change location when data is intended to be read or written. As you can imagine, this is very helpful in terms of making it so that access times are uniform and nothing weird happens. So, yeah. We would like that. Read access times from a solid-state drive are consistent no matter where we're reading from. And for that reason, actually the scheduling algorithm for SSD could just be first come, first served. It's not necessarily. Again, we could choose to put things in a different order based on priority, where we say, all right, things that are higher priority move up in the queue a couple of spaces, if that makes sense. This is reasonable considering how priorities should work in a system, but we have a choice. But it could be as simple as first come, first served. And again, to emphasize one more time, why do we care about magnetic drives when they are in the long run going away? Well, they're not dead yet. Many systems still use them. Large storage systems tend to use them. You can have much more storage for your money by getting a magnetic hard drive for something, and that's not necessarily bad, right? If this is just an archive and the data on it is not accessed that frequently, or it's not performance critical to retrieve data from it, then what difference does it make if it's a little bit slower to get data from it when it's a lot cheaper to actually have that data? Right, so it makes sense under those circumstances that you would choose to, save money and invest your money somewhere else where it would make a bigger difference. So they're not dead yet. The other thing is that anything that we learn in terms of the disk scheduling algorithms here could be used in a different context. We talk about disk, but it's sort of a convenient example for understanding a device where we have to move around to retrieve data. There is always a possibility that there's another device that resembles it, but is somehow not a disk drive, or you could take something that you learned here and apply it to a different sort of problem. Maybe if you imagine, I don't know, picking up passengers on airport loop. If you run some sort of like airport shuttle service, you could imagine this kind of algorithm could be helpful in doing that. Okay, so with the preamble out of the way, why are we doing this, and what does it matter? Here's a quick look at the hard drive internals. And a hard drive itself is comprised of, well, the platters. These are the like flat, shiny things that the data is actually stored on, and those rotate. And while it's rotating, there are little arms from the ARM assembly that have a read head, and the read head is suspended above the platter, but by a very, very tiny distance. So hard drives do come normally in carefully sealed packages. So normally you wouldn't want to open one because that's very bad for your ability to continue to use it. But if again you're able to get your hands on the one that I can bring to class, you can get an idea. Look at this; it's no damage to your own data because my own data on it is already gone. So it looks like this. The read-write head is suspended a very small distance above the surface of each platter when reading or writing, and it reads or writes data that is directly beneath it. And this gives an indication as to why sealing of the package is so important, because given the distance between the head and the platter, a tiny piece of dust is actually very large, and potentially this results in a problem, and if the disk head is going to run into it. It gets even worse if a disk head makes contact with the platter. That's called a head crash, and a head crash frequently results in data loss. So we don't want that. Now, the surface is divided logically into different circular tracks. The track is like a loop around it. The tracks are of different size. The ones that are closer to the center of the drive are shorter, and the ones that are farther out are going to be larger. They have more stuff in them. A different track is divided up into some number of sectors. Sectors are also referred to as blocks. And a set of tracks that is stacked vertically is called a column. So in the diagram, we can see there's cylinder C that consists of tracks on different platters, and they go from top to bottom. Now, your drive may or may not contain as many platters as this. You can have those that have one platter, you can have those that have 2, 3, 4. And in fact, that's to some extent how you make like a cheaper drive, right? If you buy the 2 terabyte version, it has one platter. If you buy the 4 terabyte version, it has 2 platters. If you buy the 8 terabyte, it has 4 platters, right? And then the behavior of the platters is the same. The behavior of the arms is the same. It's just a question of how many of them you have that determines the total storage of the device. So that part's easy. So when the disk is in use, there is a motor, and the motor spins the platters, and that moves them so that when we need, we can get the disk read head to the correct location. Sounds good, right? Another motor can manipulate the position of the arm, moving it from the center out towards the edge. All right, given all of this, we know a couple of things about the performance of the disk. And there are effectively 2 values that are relevant when it comes to, I would like to buy a disk, please. One of them is the transfer rate. This is how much data we can move from the disk to main memory or vice versa. And the other is the random access time, how long it takes to get to a specific piece of data. So the first part is kind of about like once we have got to the correct location, like how quickly can we get the data that is at that location into memory. The second part is more along the lines of how long does it take to get to a random location on disk. Right? If we know the data is somewhere, we've identified a target location for it, well, we still have to go there and we still have to get it. The random access time itself is broken down into 2 components, the seek time and the rotational latency. And these are both measured in milliseconds. There's kind of no escaping this. We can't, make the drives spin any faster because the platters would break. The rotational latency would decrease, but it wouldn't really help. And the seek time is about sort of moving the arms around. They do tend to run in the millisecond range, as we've discussed, and typically when we're modeling a reasonable hard drive, we're talking about like the total random access time being something like 8 milliseconds. So let's actually sort of think about doing a disk transfer, right? So what we actually see looks something like this. We're going to have to wait for the device if we need to wait our turn. That's possible. We don't necessarily count that in the time it takes to complete the request. And then we have to submit the request. That's the waiting for channel. That's where we are submitting the request, and we're sending it to the device. And then there is the seek time, which is moving the arm to the correct location, so finding what is the correct track that we are interested in. And then there is the rotational delay, which is to say that when we arrive at the correct track, the piece of data that we're looking for might not be directly under the read head right now. Right? We might have to wait for the disk to spin a little bit more to actually get here. As you can imagine, seek times and rotational delays when we talk about modeling a hard drive are averages, right? Because there is the possibility that we arrive just at the exact moment that we need, and therefore the rotational delay is 0, or we just missed it and we have to wait for a full rotation of the disk before we get another chance. On average, we will expect it's about halfway, right? There's averages built in here. So the total average access time, T sub A, for a disk operation is computed by the following formula, which is T sub S, the average seek time, again, emphasis on average, plus 1 over 2R plus B over Rn. So 1 over 2R, this is 1 over 2 times R, the rotation speed, as measured in revolutions per second. And if you buy a magnetic drive, it will say something like, it's 7,200 RPM. Well, that tells you something about the rotations per second, so that's the figure that's interesting. B is the number of bytes that we would like to transfer, so how much data are we going to read? And then N, capital N, is the number of bytes on a given track. So by combining these, right, we can add up everything that we need to figure out how long it would take to transfer some number of bytes. For a small number of bytes, we will expect it takes less time, but more of that time goes to overhead. For a larger number of bytes, the actual total time is going to be larger, but less of it goes to overhead, because like seek time is fixed. It doesn't scale with how much data we're interested in pulling, and the 1 over 2R also doesn't scale with the amount of data that we're pulling, so only the last term scales with that. Right, and this makes sense. TS is the seek time on average, and 1 over 2R is the average rotational delay. And based on that, it's easy to calculate just how much we would like to retrieve. Now, in a simple example, this disk is going to have 7,500 RPM. 7,200 is much more common, at least in my experience, but 7,500 has been chosen here to make the example math somewhat cleaner. So we have a disk with an average seek time of 4 milliseconds, so that's our TS, a rotation speed of 7,500 RPM, and 512 byte sectors with 500 sectors per track. And if we want to read a file that is the equivalent of 2,500 sectors, this makes it the equivalent of 1.28 megabytes of data. Okay, I mean, it's not nothing, right? This is a non-zero amount of data, but it's also not a particularly large file. Just off the cuff, I'm going to guess that a number of the memes in the lecture slides are bigger than that. So sure. Let's imagine that we want to pick something like that, and yes, sure enough, if I look at some of them, I'm sure I'll find some that are bigger than this. Okay, so we'll imagine we want to load a meme. Well, it matters now how the file is stored, doesn't it? Because if we want to get the data from the disk, we have to go to the disk and we have to get it, and that's a little bit like saying just go in your house and get cookies. Okay, but where are the cookies? How much work does it take to get them? How many cookies are we trying to retrieve, and where are they located? Right? Maybe you have emergency cookie stashes located all throughout the house. I mean, it's a good idea. You wouldn't want to run out of cookies or somehow be caught without cookies. So like that kind of thing matters. How do we store the data? Where is it? And how do we access it? So let's imagine then if we're going to choose the simplest option, the data is sequentially organized. So the file occupies all of the sectors on 5 adjacent tracks. So all the pieces are right next to each other. It's as if you wrote it down just immediately one piece after another, all on adjacent tracks. So to read the first track, it takes 16 milliseconds as in this example. 4 milliseconds seek time, which we established from the question description. 4 milliseconds rotational delay. This is why we chose 7500, because it makes the math a little cleaner. And then 8 milliseconds to read each of the 500 sectors. To read all of the 500 sectors. Because data is sequential, no additional seek time is necessary. So we just keep reading subsequent sectors. So there's only the rotational delay for each additional track, right? When we finish with a track, we just move to the next one. Because it's the immediately adjacent one, the time is negligible, but there is still going to be some rotational delay when we get there. So each additional track takes 12 milliseconds, because we skipped the seek time, but there's rotational delay, and there's 8 milliseconds to read that track. When we do this, we end up with a total time of 64 milliseconds, right? 16 for the initial one, because we had to go there, and then 12 for each additional track, because it's all sequential. Okay, not bad. What if instead data is randomly distributed on disk? So it's not sequential. We have to jump around on disk every time to get every single block of this data. Well, the average seek and rotation times don't change. Those remain as they were. But then we can just say, all right, reading one sector takes 0.016 milliseconds. So each read of a sector will take 8,000 of these. So 8.016, sorry, there's 2,500 of them. So 4 plus 4 plus 0.016. So if there are 2,500 sectors times 8.016 milliseconds to read one random sector somewhere on disk, we end up with a total time of 20,040 milliseconds, or 20 full seconds, as we would say in human time. And I mean, honestly, if I stopped talking in this lecture for 20 seconds, it would be kind of awkward, right? You would notice. That is a very noticeable amount of time. If I pause for 2 seconds in the lecture, you're probably thinking, oh, he's having a sip of water because he's been talking for the last 20 minutes without any breaks. If I stop for 5 seconds, you might wonder, was this an editing mistake in the program when I was touching up the lectures and removing all the wrong things, or fixing any problems that I've encountered. But if it was 20 seconds, you would probably post a comment where you said, like, hey, I think there's something wrong with the recording. I think there's some section that's missing. 20 full seconds. Or in the words of Lemongrab, unacceptable. Okay, yeah, seriously. It would take 20 full seconds to read 1.28 megabytes of data if it were completely randomly distributed across the hard drive. That's not okay. We would not consider that acceptable performance for our system. We would find that extremely frustrating, and we would find that to be just like a system that we couldn't use, right? As much as we would want to, as much as we might like the computer, we would just say, look, it's too painful. This isn't working. So the order in which sectors are read from the disk, it turns out, makes a huge difference, right? If they are not located sequentially, it's going to be very painful to read a large amount of data. We're going to talk about, in an upcoming topic, this idea of how do we store the data on disk, and that's going to favor, if you will, something like sequential allocation. But we don't have to do that. There are other strategies which are not insane, which could get the job done. Keeping in mind also that our data access patterns don't always look the same as please read this entire file into memory sometimes, like if it's a database and we're just querying one record, we just need one block. It has whatever data we were asking for, and it doesn't really matter what the other blocks on disk are or where they're stored. But we'll talk about that soon. Before we do that, and before we get too far away from the concept of scheduling, I want to talk about the idea of how to schedule the disk reads and writes. Before we do that, though, I want to introduce one more interesting metric, if you will, which we will call bandwidth. And bandwidth is the total number of bytes transfers divided by the total time between the request for service and the completion of the transfer. Right, so if we ask for something to happen, we want to download a file, and the file is 500 megabytes. We care mostly about what is the total time that it took to do. So let's say it takes 2 minutes. Then we would divide the 500 by the 2 minutes, and we would get the effective bandwidth. Right? In the network situation, we might be limited by, say, eduroam, or we might be limited by the upload of the remote server. Those things make an impact on bandwidth, but usually that's the kind of thing that we're talking about. We're talking about network bandwidth. But in this case, I mean disk bandwidth. It's a measure of how much data we're transferring in a period of time, and all things being equal, it's something we would like to improve, because again, if we're trying to load data from a file, or we want to get something or write something, the more we can do in the same period of time, the better. So when we're reading to memory from disk, or writing to disk from memory, or what have you, we have a system call, and the system call has the following information. Right? It has some information about the direction. Is this a read or a write? Like what's the source and what's the destination? The disk address for the transfer, that could be the source or the destination, depending on what we're doing. The memory address for the transfer, again, also could be the source or the destination, depending. And then how much data are we planning to transfer? And we can turn that easily into the number of sectors based on the configuration of the disk as it's set up in the system. Now, nobody actually seriously advocates random scheduling, but as per usual, choose randomly is something we ought to discuss as an option, just so we have that as a baseline against which we could compare various scheduling algorithms. It's, of course, garbage, right? We wouldn't choose that, but if you wanted to do an analysis, then it might make sense to actually include it in the analysis, just so you can say, all right, so we've actually concluded it's garbage based on our facts and figures, not just based on, well, it sounds bad. Similarly, we could do disk accesses based on process priority, paying no attention to how convenient or inconvenient it is from the perspective of the disk. The highest priority process's request always gets serviced first. And that would work. It is a viable scheduling algorithm, and it does, again, give priority to high priority processes in terms of, they get their reads and writes done faster, so they're happy with that. But I don't think that's actually all that interesting to talk about here. Similarly, if there is only one request for a read or a write, there's no decision to be made. There's no need to schedule it. If you're only doing one chore today, I just have to go to the supermarket, then you don't really have to think about, okay, how do I efficiently schedule my day around this, making sure that I don't have a lot of backtracking. You just go to the supermarket and you get your stuff and you go home, right? It's only more interesting when there's more than one operation to perform, because then we have to make a decision about what's the order in which we do it. So this algorithm that we'll start with is first come, first serve. It is fair in the sense of everyone is equal, but it doesn't necessarily provide the fastest service because no effort is made to minimize extra work done. So if you remember from the previous topic where I mentioned this idea of if the groceries and dry cleaning are in the same plaza, it doesn't make sense to go to the bank in between, just because while you're in one place, you should do all the things you need to do there. That's what happens here, right? It is first come, first served, but we don't follow that rule at all. We make no effort to go in an efficient manner. We just take whatever request we have, right? And so no attempt is made to group, organize, or rearrange the requests. And in the example that's given here from one of the textbooks, it's using an example that is perhaps on its face a little bit ridiculous, but it is constructed in such a way that you get different results for the different outcome, for the different algorithms. So we'll make it work. Right, so we start at 53, and the request queue 98, 183, 37, 122, 14, 124, 65, 67 is our basic ordering of this is the requests as they came in, and we just try to do them in that order. So when we do that, right, we start at 53, we go to 98, then we go to 183, and then we go all the way back to 37, and then up to 122, and then down to 14, 124, 65, then 67. And of course, the way that the requests have been scheduled, it results in a lot of like wild swings back and forth. And to add up the amount of movement, the work done, if you will, by the hard drive seeking around, we just take the difference between the two locations. So, 98 minus 53, and we will say, okay, it moved that many cylinders. And when we do that with each segment, we'll find out that the total movement here is 640. Okay. This example, as I say, sort of intentionally includes the sequence where it's like 122, 14, 124 to illustrate a problem, which is a wild swing back and forth over a long distance. It would not make sense to do this. If we could avoid it, we would maybe choose something else. So the next thing that we're going to talk about is shortest seek time first. And shortest seek time first is based on the idea that, well, we want adjacent operations to take place consecutively instead of just choosing the next item in the queue. So we're going to choose whichever one has the least seek time from the current position. So given a list of chores, the one that we're going to do next is whichever uncompleted chore we are closest to at this moment. Okay. It doesn't sound crazy, right? It does sound like something that could actually work. So using the same example as before, we start at 53, and the closest one by our math is 65, because it's only 12 away. From there, 67, then 37, 14, 98, 122, 124, 183. And following this routine, the total movement for the discrete head is 236 cylinders. That's quite a dramatic difference from the previous 640, and it's not surprising because we don't have a huge amount of backtracking in this regard, right? We just go to whichever one is closest. There is some backtracking. We go from 67 to 37 to 14 and then up to 98, but the total amount of backtracking is fairly limited. So this seems like it is an improvement. Of course, things aren't always quite so simple, right? This routine is subject potentially to starvation. Suppose the disk head is at position 14. While we're there, a new request arrives at 24, and that's the closest one, so we'll go do it. And then while we're there, another low-numbered request arrives, and like, oh yeah, we should do that. It's definitely the closest. And that means effectively that a request that is at a high number is going to be put off for a long time, potentially indefinitely. How many requests we have determines how likely it is that starvation occurs. Right? If we don't have very many requests, we will certainly get to all of them eventually. If we have a large number of requests, it dramatically increases the likelihood that our request that has to wait a long time gets to wait even longer. Okay. Other things that we notice about this. Number one, although it is dramatic improvement over the first come, first served or first in, first out approach to looking at this, it's not optimal. If we analyzed every option and we tried to come up with like what is the option that has the fewest amount of cylinders moved, it would actually be 208. And that would actually happen if, in this example, we went from 53 to 37 at the beginning. Why? Because it will reduce the amount of backtracking. Right? We would go from 53 to 37, we would go to 14, and then on the way we would go to 65, 67, 98, 122, 124, and then finally 183. Some amount of backtracking is inevitable. We start out at 53, and there are requests that are both higher and lower than that, so there's no way to avoid. We're going to have to do some amount of backtracking, but the most optimal possible is 208. One of the reasons why this shortest seek time first might actually be helpful is it does provide some idea of spatial locality. If there are a number of requests that are located near one another on disk, this algorithm takes advantage and will try to carry out all of those requests, hopefully relatively quickly. The next thing that we're going to talk about is called the SCAN scheduling algorithm. And what we'll do is we'll move in one direction until we reach the end of the disk, and then we'll change direction to the other way, sweeping from one end of the disk to the other and then back in the opposite direction. And this is sometimes called the elevator algorithm. It doesn't really resemble like an elevator under normal use, but if you sort of get the idea that if the elevator stopped at every request always going up and every request going down, but instead of just going where it's needed, it always ran the full length of the building, well, then it would resemble an elevator. You can see this kind of thing sometimes in airports, where like the elevator goes from 4 floors up all the way down to the basement or something, and it stops at every floor. Because that's considered kind of user-friendly for people who might not be familiar with how the elevator works or don't speak the language of the country that the elevator is located in. So something like that could work. Anyway, so what we'll do is, like I say, we just go in one direction at a time until we get to the end, and then we turn around, and then we go back. So no more zigzag, no more backtracking. We just go all the way to 0 to start with here, because we're imagining in this example that we start at 53 and it's descending. So we just collect any requests that are on the way. So that means 37, 14, and then we go to 0, turn around, and then on the way back, we pass by 65, 67, 98, 122, 124, 183, and it will continue up to 199 in this example. So this is good and bad, right? If a request arrives just in front of where we are, so like we're currently at 124 and 129 arrives, well, we're just about to show up there. So that's great. We'll be happy to sort of collect that and move on. But it could also be quite a very long time, right? If we are at 123 as the new request and 124 is the location of the disk, well, it has to go all the way up to 199 and then come all the way back to 123. And because 123 is closer to the high end of the disk, it would actually be worse if we were currently at 122. So we just missed it. So it had to go all the way down to 0 and then all the way back. This is okay. It does not take advantage of spatial locality like some of the shortest seek time first algorithm might. And if we've just moved away from an area, it could be a long time before it returns. And if there are multiple accesses in the same area, well, they're likely to be sort of spread out in time. And maybe that's okay, but maybe that's annoying. You might have also noticed here that when we finish at one end of the disk, so like we made it up to 183, we go up to 199, if there are requests outstanding, they're likely to be at the other end of the disk, right? If something was nearby, we probably got it already, so it's likely that whatever we've just finished in this area is now done, and requests have been accumulating at the other end of the disk. And that's the idea behind the SCAN algorithm. And so instead of reversing the direction and then servicing requests on the way, we jump back to the beginning of the disk, and we are always then going in the ascending direction. Okay, it's called SCAN because C is for circular. Sadly, Cookie Monster, not for cookie. And as if the last cylinder just wraps around to the first. So what we'll do is we're always going up. So we go up 53, 65, 67, 98, 122, 124, 183, 199, and we jump to 0, and then 14, 37, and we just kind of keep going, right? So again, the goal here is to always proceed in one direction, and we don't want to ever backtrack. We don't reverse what we're doing. And this kind of thing is like reasonable in terms of how we might accomplish how we might accomplish other tasks in life. We have sort of a regular patrol, and we just go around the patrol and do anything that needs doing while we're there, and that would work, right? There doesn't have to be backtracking in this regard. And yeah, why is this beneficial? So one thing that's noteworthy is that, in the previous scan algorithm, some areas are visited more frequently than others, if you know what I mean. Assume that the amount of time that it takes to scan from the start to the end of the disk is t. The expected service intervals for sectors at the periphery, so if you're at the very beginning or the very end, it's 2t, right? That's not equitable, because if you're in the center, the service time is a lot more like t. CScan reduces this and makes it more equal, so that the time is t plus s max, where t is the scan time from bottom to top, plus s max is the maximum seek time, i.e. the size of that big jump from the end of the disk back to the beginning. And there is a little algorithm improvement here called look and clook, which is improving it by not going all the way to the end of the disk, which is like when you get to the final request, so we get to 183, we don't have to do the work of going up to 199, and similarly we don't have to then jump all the way back to 0, we can just jump to the lowest request, and it just saves us a little bit of extra time by cutting off those sort of useless bits that we weren't doing anything with anyway. There were no requests there, so just skip it. Okay, so let's talk about choosing, shall we? Although we can probably agree that first come first serve is not great, how do we decide between the other options? The look approach seems like it prevents the starvation problem, which would otherwise be an issue. Although we can expect that with scan or cscan, all requests get serviced, but there is a potential that a process is effectively starved because its request at the end of the disk is constantly postponed as more and more requests come in, right? And when we talk about this, if we're scanning up from 0 and there's a request at 189, and requests keep coming in between here and there, well, we're going to keep stopping on our way to do those. So things that are far away from the disk head might have to wait an absurd amount of time to get their turn. And so a strategy to prevent this is a modification of the scan algorithm such that it has 2 queues for requests, which you can think of as being like double buffering, just as we talked about a little bit earlier. So while one queue is being emptied, the other is being filled. So if the queue contains, let's say, 10 requests, right, once we're working on those requests, other requests go in the new queue, and it means that a request doesn't wait indefinitely. Right? If a queue is of capacity C, then a particular read or write can wait at most C accesses before it gets its turn. The larger the value of C, the more performance resembles scan. A smaller value of C means the behavior is more like first come first served, down in the limit where C is 1, in which case it is exactly like first come first served. And if C is effectively infinite, then it is exactly like scan. The choice of C is a trade-off, right? We're trying to sacrifice a little bit of performance to ensure at least a baseline amount of fairness, right? Absent this, a request could wait an unusually long amount of time, but if we choose a value that's too small, we're not maximizing the performance of our disk. Now, the scheduling algorithm that we just talked about for all of these, where we talked about the number of movements of the disk head and what have you, they don't consider rotational latency, even though they are on the same order. In fact, they're even close in size when we talk about number of milliseconds. Why is that? It's because it's very difficult for the operating system to schedule for improved rotational latency. That's the disk's responsibility for the physical placement of the logical blocks. We can have an idea of where on disk in the operating system something is stored that allows us to control the seek time, but it's not very helpful in terms of the rotational latency. Thus, in practice, the hard disk controller itself is responsible for taking some of the scheduling options. If the operating system can provide a group of requests to the hard drive, then the controller can try to figure something out for how to schedule them. with that said, if the speed of reads and writes were the only thing to be concerned about, then we might say, well, why is this the job of the operating system at all? Why can't we just give the requests to the disk queue and let it figure out how to do what we asked? That would be true, except for the fact that in real life, the operating system has certain priorities that need to take precedence, right? The disk is not a super smart device in the sense that it doesn't know why something is happening. It knows there's a read or a write, but it doesn't understand, say, what is supposed to result from this read or write. Loading a page into main memory might take priority over an application writing a file to disk, right? Loading the thing into memory unblocks a program. It allows it to continue executing and makes the user happy. Writing something out to disk, like, oh, it's a log file, it's an asynchronous write, it's not that important that it occurs immediately, right? And ideally, high priority processes aren't waiting too long for low priority processes disk writes. Again, they can't wait forever. We don't want to allow starvation, but under some circumstances, the operating system really does have to manage the reads and writes and can't just leave it up to the disk controller because of the fact that the disk controller lacks the context that the operating system has. Okay, that is a wrap for this particular topic. I mentioned earlier on this idea that how we store the data is actually important in terms of performance, and so yeah, now we should take a look at that. So that's what we'll discuss in our next topic. Indicates that it's finished with whatever request you gave it. The job then of the interrupt handler is to store the data in a buffer if we were fetching data, so in this case yes, and signal to unblock the device driver. The device driver is responsible for figuring out which of the requests has completed, because there could be more than one, and indicate state change to the I/O subsystem, so device is available again, or request is complete, or queue size has decreased, whatever it is. And then we'll transfer the data to the process memory as per the request. We'll return from the system call, and then the I/O is complete, so the input data is available. When we did this with the read, from the system call point of view, we didn't really go into what the operating system is doing in the background, but I think we have a much better idea now, having talked about much more of sort of the internals and how it's supposed to work. That we now have to send it to the device driver. The device driver has to request the read from the hardware device. When the data comes in, generate an interrupt, and then transfer that data, deliver it to the requesting process. So it's a lot of steps, right? There's 10 distinct steps here, including like when the data has been transferred to the user process, we can mark it as ready to run again, such that when the scheduler chooses that process can be selected to run again and continue executing. So yeah, it's a complicated process, and there's a lot of work that has to be done to actually deliver the data, but yeah, from the perspective of the user, it's kind of transparent, right? Make your request, get blocked until it's ready, and then you continue executing when the data is there. In our next topic, we're going to talk about the disk scheduling, which I had mentioned previously. So let's leave it off here and continue there.